The next concept that we are going to look at is the properties of quadrilaterals. This is on page 66 of your workbook. Now, a quadrilateral is just a four-sided figure where the sum of the interior angles is equal to 360 degrees. Whenever you get parallel lines and equal lines between the sides, we get special types of quadrilaterals. And the first one we are going to look at is a parallelogram, or a palm. So in short, for parallelogram, we often say just it's a palm. So P-A-R-M to represent a parallelogram. Now there are certain properties that are specific to parallelograms. Let's look at them. The first one is that the opposite sides of a palm are equal. So in this diagram you can see that if we call this A, B, C, D, then AD is equal to BC and AB is equal to CD. These properties you do need to remember, and you will need to apply these properties in later questions that you get. Another property of a palm is that the opposite sides are parallel. So once again, if we have side A, B, C, D, then side AD is parallel to side BC, and side AB is parallel to side CD. So both pairs of opposite sides in a palm are parallel and equal. That's what we've got so far. Another property is that the opposite angles are equal. So once again, if we have A, B, C, D, then angle A will have the same value as angle C, and angle B will have the same value as angle D. Now, a diagonal, which is drawn from one vertex to the opposite vertex of your parallelogram, the diagonal will bisect the parallelogram. And what that means is that it divides the area of the palm into exactly two equal pieces. So if we look at the diagram, what you will notice here is that these two triangles are congruent, which means they're completely identical. And if you had to find the area of each of these, you will see that they are equal. So the diagonal bisects the area of the quadrilateral. And then an important one is that the diagonals bisect each other. So therefore, if I have A, B, C, D, then diagonal AC will bisect diagonal BD. Bisect just means that it cuts it into two equal halves. The next shape that we are going to look at with special properties is the rectangle. This is on page 67 of your workbook. Now, a rectangle has all the properties of a palm. So that means the opposite sides are equal and parallel, and the opposite angles are equal. And so it follows through. It takes all the properties of the palm, but it also has some of its own unique properties. And one of those is that all the interior angles are 90 degrees. So we still have that the opposite angles are equal. The only special thing now is that each of the angles is at right angles. So therefore, each of these sides are perpendicular to each other. And then another unique property to a rectangle is that the diagonals, so in this case AC and BD, they don't bisect each other, but rather they are equal to each other. So the length of AC will be exactly the same as the length of BD. The next shape that we are going to look at is a rhombus. This is also on page 67 of your workbook. A rhombus, once again, has all the properties of a palm, but also some of its own unique properties. One of these being that all four sides are equal in length. So it's no longer just the opposite sides being equal to each other, but each of the sides are all equal to each other. The diagonals don't just bisect each other, but they do it in a specific way. They bisect each other at right angles. So that means they are equal to each other, but this happens at right angles. So therefore, they cut each other at 90 degrees. So the diagonals of the rhombus will bisect the opposite interior angles. The next shape we're going to look at is a square. Now, a square has all the properties of both a rhombus and a rectangle, but it also has some of its own special properties. So therefore, we know, since it has the properties of both a rhombus and a rectangle, we know that all sides are equal We also know that the diagonals are equal. We know that the diagonals bisect each other at 90 degrees. So this is just following through from the properties of the rhombus and the rectangle. The interior angles all equal 90 degrees, and the diagonals bisect the interior angles. So those are the properties that it has in common with the rectangle and the rhombus. So the diagonals bisect the interior angles of the square. The special property with the square that's different from the rhombus is that even though the opposite angles are bisected, since we know that each angle in a square, each of the interior angles is 90 degrees, when these angles are bisected, they will each be equal to 45 degrees. And that's different from the rhombus, which is what gives the square a different shape from the rhombus. So if you look at the rhombus, for example, you will see that since the interior angles are not 90 degrees, it sort of tilts off a little bit more and looks a bit more like a diamond shape, whereas a square is more of a rigid shape compared to your rhombus. The trapezium is a really special shape because only one pair of opposite sides are parallel. So in this trapezium, the only pairs of opposite sides, if we have A, B, C, D, only AB will be parallel to CD. So guys, those are the properties of all the quadrilaterals that you need to be familiar with. Make sure you understand each of them and that you know when to apply which property. The next thing we're going to move on to is example 2, and this is on page 68. Here we are told that a point P with coordinates A and 2A is reflected about the line y equals x. We are then asked to write down the image point Q. Now, when you have a point being reflected about the line y equals x, what you will have is that the x and the y coordinates swap about. So normally your coordinates are in the form x and y, but if it's reflected in y equals x, your x and your y values swap around. So your new set of coordinates will be of the form y and x. So therefore, since my x value here is a and my y value is 2a, once we reflect it in the line y is equal to 2x, we are going to get the point P is 2a, so the y value comes first, and then a. We can represent this on a diagram as follows. So P is the point A and 2a, but Q, which is the reflection of P in the line y is equal to x. This is called an axis of symmetry. So Q being a reflection in that line, the x and the y values swap around, and I now get the values 2a and a. So in part 2 of this question, Q is then reflected about the x-axis, and we are asked to then write down the image point R. Now, whenever you have a reflection in the x-axis, so if I draw you a set of axes, that being your y and that being x, if I have a point in the first quadrant and I reflect it in the x-axis, all that's going to happen is your positive y values are going to become negative. Your x values are not affected at all by a reflection in the x-axis. It is only your y values that will change. If you had a negative y value and you reflect it in the x-axis, it's going to become positive, but once again, your x value is going to stay exactly the same. So we're taking the point Q, reflecting it in the x-axis, and this is how it's going to look. So Q has coordinates 2a and a. If I reflect it in the x-axis, my x value is going to remain unaffected. So therefore, these would be at exactly the same x value. So that's still going to have the value of 2a. But your y value is now going to change from positive a to negative a. So therefore, point R is going to have coordinates 2a, so still the same x value, but the y value is now going to become minus a. So r would be the point 2a and minus a when we reflect in the x-axis. Now for part 3, we are looking at a transformation that we refer to as a translation. So here we are told that r undergoes the transformation x minus 3a. So in other words, from the x coordinates, we take away 3a, and then from the y value, we add, or to the y value, we add 3a to obtain a point t. They would like us to write down the coordinates of t. Remember, the coordinates of r are 2a and minus a. So if r undergoes this transformation, we have from the x value, we need to take away 3a. So to get the coordinates of t, I'm going to say the x value minus 3a, and then to the y value, I'm going to add 3a. So therefore, this is going to become 2a minus 3a is minus a. And then your y value plus 3a minus a is going to be 2a. So therefore, the coordinates of t will be minus a and 2a. So we can represent this on my diagram as follows. Remember, all that's happened is your x value is now minus a and your y value is 2a. So that means it's going to be in line with point P. So it's going to have the same y value. But your x value is going to be the reflection of point A in the y-axis, which gave us minus a. So therefore, t will be that point in the third quadrant with the same y value as the point P, but then the negative of the x coordinate, which was a, so now it becomes negative a. The last part of the question would like to know what type of quadrilateral is PQRT, and they then ask you to justify. So let's join the dots on quadrilateral PQRT and let's see what type of quadrilateral this forms. Alright, so quadrilateral PQRT is going to have that as our basic shape. Now, before we do any sort of workings, to me, immediately, it looks like a trapezium, which means we're going to have one pair of opposite sides parallel. But you cannot say that just by looking at the diagram. You have to show some working, and that's very important, guys. If you are going to make a statement that's not apparent, you need to show your working to back it up. So while it looks like a trapezium, we actually have to prove that it is a trapezium. You will remember from the properties of a trapezium that one pair of opposite sides is parallel. So what I'm going to show you now is the working out to show that PQRT is in fact a trapezium. So we have the coordinates of P, A and 2A, the coordinates of Q, with 2a and a. And remember, in order to show that something is a trapezium, all you've got to do is show that one pair of opposite sides is parallel, and only one pair of opposite sides is parallel. That was minus a and positive 2a. So firstly, we're going to work out the gradient from P to Q using the formula y2 minus y1 all over x2 minus x1. So from P to Q, I'm going to have 2a minus a all over a minus 2a. And I'm going to get a over minus a, which would give me an answer of minus 1. So we've worked with P and Q, and we worked out that gradient. Let's now work out the gradient of R to T. So it's going to be minus a minus 2a all over 2a minus minus a. So here let's use a bracket just so that we remember to change the sign. We're going to get minus 3a all over 2a minus minus a. It's going to become 2a plus a, which is just 3a. And here my answer is going to be minus 1. So therefore, the gradient of PQ and the gradient of RT are exactly the same. And you will remember from analytical geometry that if the gradients are equal, then we have parallel lines. So since the gradient of PQ is equal to the gradient of RT, this would imply that PQ is parallel to RT. And in fact, if you were to go and work out the other sets of lines, so the gradient of P of QR and the gradient of PT, which were the opposite sides of the trapezium. So if you tried PT and QR, you'd see that those will not be parallel. So therefore, since we have just one pair of opposite sides parallel in this diagram, we can say that it is a trapezium.